Okay, we're going to continue in chapter 1, and we're going to look at recognizing sets unions as well as compound inequalities. So first we're going to work on recognizing set intersection and union, and this is going to be something we're going to use throughout the course. So I know that on first look it might not seem that it's useful, but we will be using this in domain and range, functions, graphing, and several other places. So the first thing is we have to recognize a set intersection and a set union. Those are two different ideas. If you have two sets, like you see on the screen, A and B, the set of elements that belong to both is the intersection. So if I look at these, I would have 2 and 3 are in both sets so that A intersect B, which is written with, it's kind of an upside down U, is 2 comma 3. If I'm looking for the union, union means and. So you literally read this, A and B is 1, 2, 3, 4. Notice there's a 2 in A and a 2 in B, but I still wrote the 2 just one time. We don't show repeating numbers when we're doing intersections or unions. So now we're going to look at finding the intersection of two sets. For any two sets, if I'm given a Venn diagram, the intersection visually is the area where they overlap, which is basically showing what we did earlier with it's the numbers that are in A and also the numbers that are in B. That would be the intersection right there. So if I'm given this, I want to find the intersection of A and B. So I'm looking for elements that are in both. So if I look at A and I look at B, they both have a 5 and they both have a 6. So I'm just writing this out notation. I wrote set A out, I wrote set B out, and the numbers they have in common are 5 and 6. So the intersection is 5 and 6. How is this going to apply? We're going to start using set intersections with compound inequalities as we get to the answer. So this is going to be something that's going to be important. A compound inequality is different from an inequality because there are two of them. And they're linked by an and statement or an or statement. So there's two different ways to view these. Let's look at how to do it with an and first. To do an and, we're going to solve the inequality individually, each one. Because they're joined with an and, the solution would be the intersection of the set, the numbers that are in both the solution for the first one and the solution for the second one. So let's look at this one. I have x plus 3 is less than 1, and x minus 4 is greater than negative 12. I'm going to solve those individually. So I'm going to subtract 3 from both sides in the first one to get x is less than negative 2. In the second one, I'm going to add 4 to both sides to get the x alone, and I get that x is greater than negative 8. Now to consider the intersection of these sets, I need to figure out what numbers it has in common. So if I do this on my number line, it's sometimes easier to visualize. For x is less than negative 2, that would be that set of numbers on the number line. For x is greater than negative 8, this would be this set on the number line. And if you look at the solution set, it's going to be the overlapping of those two, which happens from negative 2 to negative 8. So imagine if you just put those two number lines on top of one another, they would overlap from negative 2 to negative 8. And we're using parentheses there because there's no equal to symbol. Let's look at another one linked by an and, but we're going to use a little bit more of the multi-step solution process. The first one, I'm going to subtract 4x from both sides, so 2x minus 4x is negative 2x. Then I'm going to divide both sides by negative 2, remembering that when I divide by negative 2, I'm going to switch the direction of the inequality sign. Over here on the right, I'm going to first divide both sides by positive 3 to get x is greater than or equal to negative 3. I don't change the direction of the sign because I didn't divide by a negative number. Then I'm going to graph my sets. I'm going to use a bracket because it has an equal to. And my second set, I'm going to use a bracket because it has an equal to. And then I'm going to consider the overlap, which would be from negative 3 to infinity because the arrows pointing to the right overlap one another. And notice the solution can also be written in set notation as bracket negative 3 to infinity parenthesis. We always use a parenthesis with infinity. We never use a bracket. Here's another and example. I would subtract 2 from both sides on the left. I would subtract 1 from both sides on the right. Then I would divide by 2. So now I have my two solution sets. I'm going to graph those two solution sets and figure out where they overlap. And if you look, if I take that first number line and put it on the second number line, there is no overlap. So that means that there's no number that fits both of these, so there's no solution. So don't get thrown off when they don't overlap. That means there's no solution. So let's look at finding the union of two sets, which would be, I would have everything in set A combined with everything in set B, and notice the keyword of or. So we're going to apply this to an or inequality. So let's first just review. I want to take everything in set A and add it to A and B, set B. So I'm going to start by listing the elements, and then I'm going to add any additional elements from set B, and I'm not going to show repetition. So A and B is given below, and that's going to apply to compound inequalities with the word or. We're no longer looking at an overlap. We're looking to include all numbers from both sets. We're going to follow some very similar steps. We're going to solve the inequality individually. Then because they have an or, I'm going to include all numbers that satisfy either one of the inequalities, which is also known as the union of the solution sets. So let's look at this example. I'm going to treat them as two separate inequalities first by adding 1 to both sides on the left. Then I'm going to subtract 5 from both sides on the right. Or I'm sorry, I'm going to bring the 2x over. So I'm going to subtract 2x first from both sides. Then I'm going to worry about moving that 5 over by subtracting 5 from both sides. Now this is going to look a little different when we graph them together. X is greater than 3. There's no equal to symbol, so it's a parenthesis. And then x is less than 1. Notice these don't have an overlap. So my solution set, I'm going to write them as the first thing, negative infinity to negative 1. And we want to put them in order from least to greatest. So that's why even though it's the solution on the right, it comes first. And 3 to infinity. Notice there's parentheses around the infinities, which is a rule, and parentheses around the 1 and the 3 because there's no equal to symbol. Let's try another one. In the inequality on the left, I'm going to add 2 to both sides. Then I'm going to divide by positive 3. Because I divided by positive 3, it does not change the direction of the sign. Over here on the right, I'm going to subtract 5 from both sides. And I get, these are my inequalities, which I'm going to graph, and I'm going to use a bracket. If I look at every number that is less than or equal to 5, every number that is less than or equal to 2 is included in that set. So, in that way, my solution is negative infinity to 5. Notice negative infinity comes first because it's smaller. There's a bracket because it equals 5. Let's look at one more example. I'm going to solve it by adding 2 to both sides, dividing by positive 3. This time, I have a set where I'm looking at numbers that are less than 5, but greater than 2. So see, even though I've drawn this on one thing, the actual set is occurring and it's covering all parts of the number line. Do you see that? So that means that all numbers, because if I'm looking at all numbers that are less than 5, but greater than 2, that's an arrow going in each direction. So all real numbers are a solution to that set, which we would show as negative infinity to positive infinity. Here is an application of this. So in the lab, occasionally we see 1 or 2 word problems. Here is an example of a word problem. If we want to list the elements of each set, I would have the set for U.S. exports to country and then the set for U.S. imports. The set of countries which exports were greater than 150,000 and imports were less than 150 million would be shown here. And if I look at those conditions in that table, I don't see anybody that meets both qualifications because and is meaning we're having to look at both qualifications. There's no country that satisfies both of those conditions. So I don't have a solution here. But if I look at the set of countries where exports were between this number or from imports that are greater than 300,000, I have China, Japan, Canada that meet that criteria. So when we're looking at conditions, if it's an and, it has to meet both the conditions. If it's an or, it can meet one or the other condition to work on the set.